So before we go to statistical mechanics, I want to give you a review of thermodynamics, or what I'm going to call classical thermodynamics. It's basically just another name for thermodynamics, okay? So today we are going to start from a review of classical thermodynamics. And I'm going to use as my the guide. I'm using several sources, but mainly I will be using David Tong's lecture notes, okay? From Cambridge, David Tong's lecture notes. The link is given in the WX. This is, I think, chapter 4. Now, the idea is that, thermodynamics predates statistical mechanics. Or in other words, thermodynamics was formulated. So it'll be like maybe 2 or 3 classes, maybe even more, that will be dedicated to reviewing thermodynamics. Yeah, anyway. Okay, before I start writing things down, let me just ask you, like all of you had some thermal physics, right? So you should know some thermodynamics. Is that correct?
Yes, sir.
Okay. Yeah, we did it last semester, I think.
Yeah.
Yes, sir.
Even if you did it, it doesn't hurt to see it again.
No, not at all.
Yeah, because it's a very, it's not difficult. It's a very subtle subject. There's a lot of subtleties there, and it's understanding thermodynamics is actually quite a challenging thing. Okay, so let's carry on. So thermodynamics, or the classical thermodynamics, was formulated, before the molecular / the atomic, picture of matter has been established. Quite amazingly, this molecular or the atomic picture of matter was not accepted until the 20th century, even though the idea of atom comes from the ancient Greeks, right? So thermodynamics, as formulated in the 18th and 19th century, is completely agnostic about the microscopic constituents of matter. Like, it doesn't make any explicit reference to what matter is made out of. And, people knew that, for example, fluid was made out of stuff, but whether that stuff was at a very small level, molecules or atoms, was not something that was well known. And in fact, the icing on the cake, the paper that really helped establish the molecular property of matter was written by a very famous scientist in the 20th century. Do you know who that scientist is?
Oh, was it Boltzmann? I'm not sure.
Well, Boltzmann couldn't prove it. He developed all his theory. He developed statistical mechanics on the idea, on the basis of the assumption that there was molecule. Even people say that the reason Boltzmann committed suicide is because he was so frustrated by the physics community that they would not accept the molecular hypothesis.
Was it Dalton?
Dalton was very, very old. I mean, no, it was 20th century physicist.
Was it Einstein?
Yes, it was Einstein. in 1905, Einstein wrote 3 papers. One was on special theory of relativity. Another one was on photoelectric effect, which explored the quantum nature of light. And the other was about Brownian motion, in which he used the idea of random walk. So Robert Brown was a priest/biologist who many years ago, while he was looking at very small, like tiny, I think biological matter suspended in liquid, and what he saw was that as the size of the particle got smaller and smaller, they at some point they started exhibiting random motion. They had an overall motion down in the downward direction, which is of course natural given that there's gravity. But apart from that, there was also this kind of this random motion that like a random walk, and and even though in the same liquid, if you had some bigger fluid drop, that would just drop very, very, very smoothly. The smaller particle would not. And what Einstein found is that this is related to the Avogadro's number and the fact that the object in question is large enough to be seen by a microscope, but small enough so that if the molecules of the liquid hitting on it from all sides on average is not the same. So the momentum imparted on it from all sides is not the same at any moment. Therefore, there's always like a little imbalance in the momentum. And Einstein showed that if the Avogadro's number were to become infinite, then of course this random motion would disappear. So yeah, Einstein's contribution went beyond just what popular science kind of gives him credit for. All right, so although we will make some reference to the microscopic point of view in this review of classical thermodynamics, but I'm actually going to follow David Tong and try not to make any explicit reference to the microscopic point of view, so that it remains, our review of classical thermodynamics remains a kind of a logically, a logically self-consistent, body of knowledge. Okay. So let's start with some fundamental concepts. Okay, so one of the first fundamental concept is that of a simple system. Okay. So what is a system? A system is basically a subdivision of our universe. And a simple system is essentially a macroscopically homogeneous, it's a macroscopically homogeneous and isotropic and chemically inert and sufficiently large system. Is sufficiently large. That's a simple system. So it's a system which is, so what does homogeneous mean? It means that if you are, if the large system, so this is say the system, if you translate within the system, then the system looks the same, okay? So that means what is mean to be homogeneous? That every point is like every other point. So for example, this part doesn't have more density than this part. Okay, isotropic means that it looks the same in all directions. So it doesn't matter if you're looking at north or south or east or west, the properties of the system are the same. So that is what isotropic means. Chemically inert means that there is no chemical reaction going on and it's sufficiently large. Okay, so this is a simple system, and most of the time
sufficiently large কখন হবে না?
So essentially, what it means is that we will see that for gases, for example, gases, the independent variables that we will need to specify the gases would be, say, P and V, the pressure and the volume. We will see that everything else for inert gases is actually not independent. So now this is like, these are called state variables. And suppose that you start your experiment so that the pressure and the volume of the gas is here, and you want to get to here. So that means that but if your system, the volume in some units is, say, this is, say, 1, 2, 3, 4, 5. But suppose your volume, you took a system whose volume is not that large, but its volume is 3, right? Then it's not sufficiently large. So if you want to do an experiment in your state space where you want to span these points, then you have to make sure your system is large enough for that, right? So I mean, there might be a cutoff somewhere here in terms of volume that, you can't really go beyond that, but you're not interested in doing the experiment beyond that point anyway. Okay, so this is more of a technical assumption. Okay, so composite systems, on the other hand, and most of the time we will be dealing with, things get interesting when we have composite systems. Composite systems are systems which are made out of simple systems, but separated by, made out of, I will give you the lecture notes so you don't have to actually take notes. Made out of simple systems, but they are, separated by walls or constraints. Okay, what does it mean? So for most of the simple systems that we will be dealing with, they will be fluids, okay? So our simple systems would be fluids. There are other examples of simple systems, such as, say, a magnet. Okay. Now, we will be using fluids, meaning most of the times we'll be using gases. So gases are very easily compressible, whereas liquids usually aren't. Well, water isn't, but yeah. So composite systems, there are different kinds of walls. So for example, there are what are known as adiabatic walls. Okay, so what are adiabatic walls? So adiabatic walls are walls which do not allow the flux of energy in the form of heat. Okay, so that they do not allow the flow, which is called flux of, say, energy in the form of heat. So if you have two simple systems and they're separated by an adiabatic wall, then no heat may pass between them. Okay. If the wall is such that heat is allowed to pass, then such walls are called diathermal walls. Okay. Right. So a diathermal wall allows heat to pass. But it may not allow stuff to pass. By stuff, I mean like the liquid, the fluid, or or whatever this fluid is made out of. And if that is the case, then such a wall is called an impermeable wall. Okay, I mean, these are kind of common sense ideas, but yeah, just to get some of the language going. Okay, so next we have a very important idea, the idea of thermal equilibrium.